Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. So I'll be talking about sampling techniques for constraint satisfaction. Most of the techniques that I'll describe will be on set, but these techniques can be extended to beyond set in other domains. This is joint work with Supratik Chakrabarty, Daniel Fremont, and Sanjit Shashya from UC Berkeley, and Moshe Vardi from Rice. Just a brief motivation. In this 21st century, one of the things we design very complex systems, and a few of the things all of us are concerned is that how do we guarantee that these systems indeed work as we design. And this leads to a lot of work in the verification. Let's start with a simple motivating example. So let's say we design a simple circuit which takes two inputs A and B. This is a toy example, and C is the output such that C is some function of A and B. In this case, how do we verify? Well, one of the ways that if we can try for all possible combinations of A and B, then it's going to take long time. And what this has led to is a dominant paradigm based on simulation. So what in last 2 decades, what is the dominant paradigm is that you take a hardware design and you try with test vectors. So you have some vectors that you try, and these test vectors should represent different test scenarios. And you hope that you will catch the bug. You have some criteria, some coverage criteria. You say that, if I have tried 5% of all possible test vectors, then I'm happy, or 5 days I'll be happy. So in this case, the first question comes: how do we get these constraints? These constraints come from designers, from past experience, users. Your designer might say that I don't have a lot of confidence when B lies between 100 and 200. So this is your one of the constraint here. From past experience, you found some bugs, or your users have some constraints. So in this case, one of the things that we are interested in is that given this set of constraints, we want to sample the values of A and B in this case, which satisfy this set of constraints. And what kind of sampling we want? Well, initially, let's start. We want uniform sampling. Why uniform? Because we want to ensure that we are not missing one of the test cases trivially. So we, in cases where we are interested in covering all possible cases, we don't want to miss one of the possible test vector trivially. So to summarize, we start with set of constraints. In our case, we assume we can convert this into a set formula. And now the problem reduces to that given a set formula, can one uniformly sample solutions? Because enumeration is a harder problem, we are interested in coming up with techniques which do not require enumerating all possible solutions. And of course, whatever techniques that we want to propose should scale to real world problems. This is what we call a scalable uniform generation of set witness. Witness signifies a satisfying assignment, and we want these techniques to be scalable. This is certainly not a new problem, and it has lots of applications in other areas. For example, sketch-based synthesis, which have been based on templates. There has been a lot of work recently that can be benefited from scalable uniform generation, and there are other problems in other disciplines. I'll just illustrate how sketch-based synthesis can use uniform generation. So in what we do in this sketch-based synthesis, recently we have some sketch, which is a template of the program, and some correctness condition. There are large space of programs that satisfy this correctness condition, and usually the goal is to get an optimal program. Optimality can be in terms of running time, memory, and one of the technique is that if we uniformly sample from this space of programs, we actually have probabilistic guarantees that we will end up with a optimal program in expected number of iterations. I won't go into detail that how it can be used in other areas, but let's start with I'll introduce the sampling techniques through the uniform generation, and then I'll discuss that how these techniques can indeed be extended to other problems like model counting and bias sampling, and all of these techniques actually depend on hashing. So I'll have some discussion of hashing and what I think are future interesting directions from this work. Cool. So uniform generation. Uniform generation is again not a new problem. There, since 1980s, there have been lots of work in theory and practice. To categorize the work from academia, there are two lines of work. One is theoretical work, where the focus is to get really strong guarantees. So the foundational work by Bellare, Godrich, and Petrank in 1998, where they are actually able to give the guarantees of uniformity. So what is a uniformity guarantee? You want to ensure that the probability a sample is output should be equals to 1 over the total number of samples. So they can give the guarantees of uniformity, but unfortunately it does not scale beyond formulas of 20 to 30 variables, certainly not what we are looking for. On the other line, there has been work on coming up with heuristics, where there are very weak or no guarantees, but these methods can scale to large formulas. One of a notable work has been from was XOR sample prime from Gomes, Sabharwal, and Selman from Cornell in 2007. And industry has its own techniques to categorize the techniques. Again, on techniques that are theoretical guarantees, there are techniques based on BDDs. So you can construct a binary decision diagram from this set of constraints, and now finding a uniform solution is just doing a random walk over BDD. Well, if one can construct, we can get good guarantees. BDDs are known to blow up after the formula goes beyond a few thousands of variables. Also, there are techniques based on introducing heuristics in the set solvers. So what other people do is that in the set solver, when you are trying to find a solution, you can have introduce some randomness and then hope for and that the samples are uniform. These techniques have absolutely no guarantees. Some of the techniques have very weak guarantees, although they have strong performance. So what we are interested in is coming up with techniques that have strong guarantees and strong performance. And that is precisely our contribution. I'll introduce our algorithm UniGen, which has strong guarantees of uniformity and scales to formulas with hundreds of thousands of variables. So how do we do it? Well, let's assume the circle to be a set of all possible assignments. And the dots here represent every dot represents a satisfying assignment. So here's a wild idea. If I can partition this space in such a way that every cell that is defined by these lines has roughly equal number of satisfying assignments. If such a thing can be possible, then what I can do is that I can pick a random cell and pick a random solution from this cell. So if all the cells have roughly equal size, then for every solution has roughly equal probability of generation. Looks like a good idea, but the problem is that how can I partition without knowing the distribution of solutions? And the answer to that comes from the techniques of universal hashing proposed by Carter-Wegman in 79, further work by Sipser in 83. So I won't go into too many technical details, but a brief overview of what universal hashing does. So traditional understanding of hash functions is that we map from one space to other space. We'll call it mapping from 0, 1 raised to n to 0, 1 raised to m. So we have 2 raised to n elements, and we are mapping to 2 raised to m cells. So we know that if the inputs I have are random from this space, then all the cells where I'm mapping will have roughly equal number of elements in expectation. What Carter-Wegman showed is that it is possible to come up with hash functions for which you can have the guarantees that no matter whatever the distribution and adversary or the person who is giving us these elements choose, all the cells are still going to be roughly equal in expectation. However, that is still not good enough for our case because, for example, few more notations. F is the formula, and I'll be using RF to denote the solution space. So in this case, and that's the other one is 0. So in this case, if this is how my hash function is dividing, then the expected number of elements in a cell are RF by 2. But I might end up choosing this cell where I will not have any solution. And this is not good enough for what I was proposing earlier. And turns out that people realize this problem in other disciplines.
In the previous slide, what is RF?
RF is the set of all solutions for the formula F. And so F is the formula, and I will use RF to denote the set of all solutions. So this motivates us to come up with hash functions which have stronger bounds on the size of the cell, how many elements can be in a cell. And this led to a lot of work. The problem arose in other disciplines, so this led to a lot of work on higher universality hash functions. So we will use HNMR to denote family of R universal hash functions. So we started with universal, but now we want higher universality. Not going into too many details, but what R universal hash function means is that higher the R, there are stronger guarantees on the range of the number of solutions in a cell. So we are trying to minimize higher moments, variance or higher moment. Of course, there are no free lunches. As you want more guarantees, you will have to construct these hash functions, and R-wise universal hash functions requires a polynomial of degree R minus 1. So there's a tension. We want things that are scalable, so we want lower complexity. For that, we'll need lower universality, but we also want and stronger guarantees. And again, idea of using hash functions is not new. Bellari, Godrej, Petronk used this idea in their paper. So we said, well, let's just implement the paper. So what was the idea? You start with the solution space, which n is the number of variables in the formula. We are talking about a Boolean formula. So we have n universal hashing. So Bellari BGP uses n universal hashing, and then what it checks is that it checks whether all the cells are small or and equal.
So if you just take a formula, right?
Yeah.
What are these regions?
So these regions are specified by so there's a formula and conjuncted with the hash function. So a hash function. So additional constraints. So since the algorithm required that all the cells should be small, once you can ensure and all of them are equal, you can pick one of the cell. Well, when we try to implement, the first question came that how we are going to be able to encode polynomial of degree n minus 1. We are interested in formulas of degree 1000. So encoding a polynomial of degree 999 and giving it to set solver and asking for solution is way too much. What we have been able to show is that this can indeed be achieved just using 2 universal hashing or 3 universal hashing. So the 3 universal hash functions are simple XORs that I will discuss later. The second question is that while it can be formulated in an NP query, if there is a cell which has more solutions, it is again not feasible. So we ask, can we just randomly pick a cell and make our decision based on that cell? If that cell is small enough, can we assume something more about this space?
So I didn't understand. Like for, let's say, would cryptographic hash functions satisfy n universality? What I don't understand is, are you trying to make the hash functions more easy to compute? Or
so yeah, again there's a tension. If higher the universality, it gets harder to compute.
And will like cryptographic hash functions be good enough for your purpose?
It depends. We know that some of them are 4-wise, 5-wise independent. So like tabulation based hashing is 4-wise independent. The universality and universal hash functions, I think the only technique we know is coming up with these polynomials, which are also related to characteristic polynomials, but they require degree of n minus 1.
Yeah, okay, so you want like sort of n-wise independence.
Well, that was the idea, but we want stronger independence, but we don't want to encode polynomials of degree n. And what we have been able to show is that you don't have to go that far. You can actually achieve this using very simple hash functions. So coming back to what I was describing is that the BGP required to check if all the cells are small and equal.
So of course, there's a small price that you pay for that. To going from N to 2.
Yeah, I'll discuss that. So what we can say is that we can actually just pick a random cell and make our decisions based on just picking a random cell. And well, we don't get uniform generation, we get slightly weaker guarantees, but I'll discuss later that these are strong enough for all practical applications. So we get guarantees of near uniform generation that I will discuss later. Yeah.
Can I ask a very simple question?
Yeah.
When is actually the set solving part done?
So basically this cell can be specified by a random constraint and the original formula, so the set solving part is done here. Okay, cool. So what this has allowed us to take a method that could scale, that could work only for a few tens of variables and take it to thousands of or hundreds of thousands of variables. So coming back to the idea, there are two questions. One, how large these cells should be. And what do I mean by the size? How many solutions a cell should have? The second question is that how many cells should I partition into? So to address the first question, few things. I know if the cell is too large, then I will have to actually enumerate the number of solutions. That's what we started with, that once I figure out a cell, I'll list all the solutions and pick one of them randomly. If it is too large, then it will be hard to enumerate. If it is too small, you can see that the variance can be high. If the cell size is just 1, then the variance can be 0. Some cells might not have a solution, then it can be higher. Also, the guarantees that we gave are near uniformity, basically approximation. So the more you want, the closer to uniformity you want, the cell would be large. For example, if you want true uniformity, then you would just pick the whole solution space is your cell.
So one question I have is that you would the implicit assumption is that you would pick the region without regards to the formula. Is that how your technique would work? You would pick the region without considering the formula. And
Yeah.
once you are inside the region, you would put the region as a constraint and then go to SAT.
Yeah.
That's what you want
Yeah.
to do. Where are all these polynomials? There's all this discussion about polynomials going on. Where are
So the constraint, the way you specify the cell, because we have to come up with these constraints of hashing constraints, if we had to encode n universal hashing, then it will be formula and a degree of n-1 polynomial encoded into set. So that's where the polynomial come from.
So you need some random constraint. You just generally pick some random constraint. You're not going to get the guarantees that two things picked up are. Because what we need is that the random constraint should partition the solution space. And then I'm just going to pick up one of those randomly and pick something from there. But now I also need these guarantees of the probability that any solution I picked up is equally probable. The conditional probability that one of them is picked up, given the other one is picked up, is the same as the probability that's required. So you need these additional properties on the hashing function, on how you partition. So that is what the universality is.
Okay, so what we have been able to come up with is, I'll use pivot to denote the size of cell, and pivot is of course inversely proportional to epsilon, which I'll discuss later, which is the approximation guarantee. Typically the pivot comes down to be 40. So what we are interested in is a cell that has 40 solutions, at most 40 solutions. Okay, so let me discuss how does the algorithm look like. So the next question was that how many cells we should partition into, and for that we have a linear search algorithm that can be optimized later. I'll discuss that later, but let's start with the idea. So we initially give the formula to a set solver, and we ask if the number of solutions are less than pivot. To do that, you can just enumerate solutions. Given a set solver, you can block a solution and ask for next solution. Because the pivot is small, it is possible for most of the set solvers. If the answer is no, then you put one constraint and it partitions into two cells. You pick a random cell and you ask again. And if the answer is no, you keep doing until you reach a point where, because you keep partitioning, so at some point you reach a point where the number of solutions are indeed less than pivot. In that case, you enumerate the solutions which you have already done because you are using a set solver, and you select a solution randomly from from this cell. We are not making any assumption on the set solver as long as it's a complete solver and gives a solution. We are not making any assumption on the randomness of set solver.
So this is the number of solutions for a randomly chosen region.
Yeah. Yeah.
But there could be many regions which are greater than the width. That's okay.
Well, because we only choose one. So the whole idea is that at every point when it didn't, the number of solutions were greater than pivot, I actually partitioned into further. I said, the partitioning into 2 is not a good idea. So let's partition into more. So I actually partition into 4. I'll show XOR constraint. They actually partition, M constraints partition into 2 raised to M cells.
So one question I have is that when you go from go back to the previous slide, when you go from one constraint where actually the number of solutions were more than the pivot, when you added more constraint, you are not actually refining the partition. You are just picking a new partition, is it? Or is it just a figure that you're drawing?
Well, actually, it can be shown that you can just work with this partition.
And then refine it further.
Yeah. So you can.
Or it doesn't matter. You just saying maybe add more constraints. Is all you're saying.
So you can do either case. We initially started with saying that you have to pick the whole thing randomly, but you can actually just partition it.
Finally, it will be the case that each region in this partition will have roughly the same number of solutions.
Yeah, that's what our proofs depend on, but we don't check further. At this point, what we say is that
this procedure guarantees that.
Yeah, and there will be theoretical guarantees.
What the algorithm checks actually is that region has
Less than
small
your
solution.
Yeah.
The algorithm doesn't do anything about the
But it's
algorithm.
quite possible that you do this and there are regions with
With low enough probability that
Yeah.
can happen.
that can happen.
But it is with low enough probability, so that we can.
And that's your experience in practice as well.
Yeah, in practice it's actually much better than the theoretical guarantees, significantly better.
Yeah.
But the theoretical guarantees are that when we pick up one of these using these 3 universal hash functions,
Right.
pick up one of them and find that it is small, the probability that the samples are not uniformly distributed is very small.
Okay.
And later you're going to talk about how to get particular distributions as well.
Yeah. So what does this give in theory? Well, for uniformity, we are interested in a solution y. For every solution y in the solution space, ideally probability of y output would have been 1 by RF. In our case, we give lower and upper bounds. And these look very similar to the PEG bounds, except the constant is 6.84 instead of 1. But what I want to state is that this is strong enough. It guarantees that you are not going to miss a solution trivially.
So the pivot size is actually independent of the number of solutions of the formula, right?
Yeah.
So the number of iterations that you will take to actually reach the fixed point, like where number of solutions is less than pivot, would be very high if there are large number of solutions to the formula.
Yeah.
So why not make the pivot size actually dependent on the number of solutions, or maybe it's related somehow to the number of solutions so that you reduce the number of iterations?
Well, the first thing is that you don't know the number of solutions. Have absolutely no idea about the number of solutions. The second, you can make the pivot large and it will come down quickly. But when you make the pivot large, there's a trade-off because now you have to enumerate more solutions. So to give historical context, the BGP algorithm also had the concept of pivot, but it was n square in the number of n, where n is the number of variables. So if you have 1,000 variable formula, you have to enumerate 1,000,000 solutions. Just not feasible. It's a probabilistic algorithm, so in theory we can prove that the algorithm will succeed with probability 0.52 because it is possible that by the time you have partitioned there are no solutions in the cell you chose, and in that case we declare it has failed. In practice, the success probability of all the experiments we have run so far is far greater than 0.9, very close to 1. So Of course, we are still in the same complexity class. We make polynomial number of calls. The problem is in BPP to NP, and our algorithm is in the same complexity class. Okay, so how will we do when we go to practice? So we wanted to first evaluate how good are we in case of uniformity. So we took a small formula where it is possible to enumerate all solutions so that we can have an ideal sampler. So in this case, I'm plotting graph for a formula that has 287 variables, 1200 clauses, and has 16,000 solutions. So what we did is that we had the ideal sampler and oversampler, and we wanted to see, this graph says that the point here implies 228 solutions were generated 150 times. So
I don't understand. What is the x-axis and what is the y-axis?
So a point here, I guess if we go by the what does the point here implies, it says that 228 solutions were generated 150 times. So what we did, we ran these algorithms 4 into 10 raised to 6 times, a lot of times, and then we found that how many times a solution is generated, and you can prove that if you start with a uniformity, this actually comes to a Poisson curve. This is how it should look like.
So basically, the x-axis consists of all the solutions of the formula, right? And the y-axis consists of the frequency by which each
No,
solution
it's not.
So you make a point. Let us say you take the point 228, 150. So it means that there are 228 distinct solutions, each of which appears 150 times. So, ideally, all of the solutions should appear exactly the same number of times.
But
Even if you took an ideal sampler, you'd really get a Poisson distribution. So we're just doing this finitely times.
so if I did not tell you that which of the curves correspond to our sampler and the other one is to the ideal sampler, I guess you would be hard pressed to answer. And in this case, yeah, the yellow one is our sampler and the purple one is the ideal sampler, uniform sampler. We also tried with other metrics like LL1, LL norms, and in all the metrics that we have tried so far, the distributions for all the benchmarks are indistinguishable from uniform. Okay, so how will we do in by running time? So I'm presenting for a subset of formulas. These come from different verification scenarios, and on the y-axis the time is presented. The purple corresponds to XOR sample prime.
Going back to the previous slide, this behavior is across all benchmarks, or did you find benchmarks where you did work?
No, so far, I mean, we couldn't try for all benchmarks because we had to run it.
Were there any situations where you did have a problem? Because you are, after all, an dynamics procedure, right?
So far, we haven't had. And the thing is that because the theoretical guarantees in practice, there has a lot of work on XOR. They are far more powerful than 3 universality.
And you're also going to show some results on scalability also, I presume, later.
Yeah. So this is what I was showing here.
So there must be cases where the universal sampler finds solutions and where you don't,
right? Uniform sampler?
Yeah.
No, actually we don't have. Because we are repeating it a lot of times, so all the
statistics we have to see whether it is uniform or not. We have to run it a large number of times. So, yeah, so maybe the interesting point that comes out here is that so there is no solution which is being left out in this 4 million runs. Whereas when we tried a similar experiment using that XOR sample, right, there was a band of solutions which just got left out. So whatever the bias of the solver and other things coming in. So those solutions never got generated. Actually.
So how would those curves look like? Suppose you draw a curve for XOR. In this solutions is frequency. How would that look like?
So, well, in this, we drew this uniformity curves. In that case, you could see that the solutions were never generated. In this case, it will be some of the solutions will appear more times, and there will be less number of solutions that get appeared.
So here, that x-axis starts from 184, but it really should start from 0.
Yeah.
Right? But there are no points below whatever 184. Whereas over there you'll find that a large number of solutions are actually appearing 0 times.
And does the perhaps a silly question, but does the input format matter? I mean, everything's in CNF and something.
Yeah. So all the discussion that I'll be doing, it's a CNF.
And does it matter for your technique? I mean,
well, we use
Boolean combinations, for example.
So we need a set solver in all these techniques. So as long as your set solver is complete, it can give you a solution when you want. The algorithm doesn't care.
Okay. And what are there formulas which are larger than this?
Oh yeah. So for this, because we wanted to run a lot of times and get some compare with it, we can scale to the latest, largest we have been able to scale are 400,000 variables, 480,000.
How long did it take?
Well, again, it's
To get this curve.
this curve is every sample for UniGen gets generated in 0.02 seconds or 0.2 seconds. I mean, we ran it on the cluster and didn't have to worry at all about this. So this is very easy formula. Okay, so how well we compare with XOR simple prime, that is the solver that has some very weak guarantees compared to UniGen. The solver like BGP, which has very strong guarantees, does not scale, cannot solve any of the benchmarks that I'm representing here.
What is the what is the curve for XOR sample look like? The previous one.
So there are some solutions that were never generated. So 0. There. Not in these slides.
But it's nowhere close to this.
Yeah, I mean, if you use LL1, it's very, very different. Any of the measures you use. So that.
So Aditya, to answer your question, I think I have it on my laptop. It's
Okay.
charging.
Okay.
So the other plot that we did was to actually sort of do a kind of scatter plot, seeing that are all the solutions. So there we plotted the different solutions along. So like what Sriram was saying, so the x-axis is 1 point is one solution number 1, solution number 2, solution number 16, and then we plotted how many times it's coming. So
That should be a uniform one.
yeah, so ideally it should be a straight horizontal line.
Right, yeah.
But I mean, using finite number of samples, you'll never get a straight horizontal line. That's the limit. That's what you get. So when we ran our algorithm, so we basically get a clustering around that line. But when we run XOR sample prime, it's a very funny thing we noticed. So this line is here, the ideal line. There was a group above it, there was a band above it, there was a band below it. And on the x-axis, which were representing the individual solutions, there was an entire empty band, which means those solutions never got generated in the run sample.
Is there a reason why this kind of graph is better than that kind of graph?
So we did it. Well, you represent both. It's just both are overlapping with each other. So because these distributions, you use LL1 or whatever.
That's just what was
In our first.
Also, but then actually looking at the graph also, I mean, it's only some very high level visual intuition you get. So I mean, this is a question which we do not know how to exactly answer. How do we measure the uniformity in a practical experiment? So we tried KL divergence from the expected things, some L norms, and we plotted those bands, we plotted this, and everywhere it looks close to uniform.
So basically, I should say this is not a sufficient condition. This is actually, all of these are various perspectives on somehow viewing a uniform sample.
Yeah.
That's what my confusion was initially. So I thought this was somehow like a sufficient condition.
No. Again, we have the theoretic.
Because we had that diagram, then the next one we thought maybe we should put another kind of diagram.
So.
But I mean, really, in a practical experiment, how do we measure how far we have very objective?
Okay, cool. So how will we compare with XOR simple prime? The purple represents the time taken by XOR simple prime. The blue is by UniGen. This is log scale, and you can see even.
Bad algorithm.
That's the best algorithm out there to compare against. So I won't call bad
Different
algorithm.
answers, right? So what does it mean to compare?
No, but he's saying, but even the heuristic one is actually not as fast as what you're saying. And
Yeah.
that's how I'm thinking about it, right?
So we can actually give.
I mean, you already established that by saying that you give wrong answers. Now, are you telling me that? Yes, one, yes.
No, both.
Faster and more accurate.
Yeah, answers are correct.
So the answers are not correct here.
The XOR sample, I thought.
XOR
gave
sample
you
gives wrong,
wrong
like
answers.
Supratik said, the regions.
No, it
It doesn't generate.
generate, but it never says that you.
So it's not. It is not uniform in that sense.
Yeah, so
but
then-
whatever solutions it's giving
No,
us.
not. The problem is not about the solutions, right? The problem is about the
Uniform.
distribution of the solutions.
The distribution
and
is
that's
certainly
wrong, right? So
That scalpel
Yeah.
show you
Yeah.
bands there which are
yeah.
So, but actually, the way I think about it is that even then, even though XOR sample is heuristic, you don't lose time by going to a correct number. That's how I
Yeah,
think
yeah.
it's saying.
Great. So now I introduce our techniques using uniform generation, and I'll discuss that how we can use this to do solve other interesting problems like model counting, and when instead of uniformity you are interested in some distribution of our solutions. So what I'll be discussing is approximate model counting. So what is model counting? To define, we are given a set formula, and RF again denotes the set of all solutions. So the problem of sharp set, which is counting the number of solutions, asks what is the cardinality of RF. For example, if F is A or B, RF is 0, 1, 1, 0, 1, 1, and the number of solutions that you give is 3. And sharp P is the class of counting problems for which for the decision problems in NP. So why are we concerned about this application, this problem? Well, it has lots of interesting applications. For example, Bayesian inference can be reduced to model counting, probabilistic reasoning, multi-agent reasoning. There are lots of reductions from interesting applications to model counting. So now it looks pretty obvious what I am going to do. If I can partition, if all the cells have roughly equal number of solutions, I can actually pick a random cell, and my estimate would be the number of solutions in this cell multiplied with the total number of cells. And
So one thing that's not very clear is that can you actually count the total number of cells? Because just by this visualization, right? Certain number of cells might be outside the constraint.
no,
Yeah, but that is fine. So at every constraint you put cuts it in half. So if you put n constraints, there are 2 raised to n cells. For a particular choice of random constraint, some of those cells may be empty. But these are random things, right? So in the expectation, they are not. So there's an expected size of the cell.
So total number of cells is like 2 to the n.
It's
Yeah.
exactly 2.
yeah, so I'll show later that every XOR is 1 cell and M are 2 raised to M. So in this case, again going back the idea, we'll keep putting XOR constraint, we'll keep checking if it is less than pivot. The moment it is less than pivot, you count the number of solutions in the cell, you know how many XORs you have put, so multiply it with 2 raised to M. This gives an estimate with some confidence. If you want to amplify the confidence, the usual probabilistic techniques, you can repeat the algorithm t number of times, where the t depends on how much confidence you need, and then we take median of these values, and it can give the epsilon delta guarantees. So what does those guarantees look like? We start with the algorithm takes formula F. You can specify the tolerance, which says that how far the approximate count can be from the exact count, and the confidence, how confident you want to be. So we have a theoretical guarantee that if the counter returns the count C, then it lies within the tolerance epsilon with confidence delta that you specified. And again, the algorithm lies in the same complexity class BPP to NP. It is polynomial with respect to the parameters given access to a set solver. Okay, so how will we do in practice? We wanted to compare with the exact counters. So the cache is state of art exact counter. So what we did is that we took a set of benchmarks. We listed the running time on y-axis. These are the benchmarks. So what we see are there have been lots of development in exact counting. It can indeed do exact counting for lots of for a large class of formulas, but then it starts timing out. And what we are showing here is that the algorithm ApproxMC can handle problems that lie beyond the range of exact counters. So if you have an exact if you have a problem, you can. If you can't do exact counting, your best bet is to do approximate counting. If you can't do that, then you go to methods which have no guarantees.
So this other tool, was it by?
This is by Paul Beam, Henry Kaus, Tian Seng.
And did you also try out Latte, for example? There's the other tool called Latte, right, which is a model counter.
Latte.
Yeah.
How do you say?
It's a tool for counting.
For a given for
Model counting for SMT.
So I am not aware of the tool, but these experiments are for SAT, so I didn't.
Group is it?
UCLA, right?
That's for SMT. Probably for SAT it might be slower. Right?
Oh, are you, well, they have the other.
On a SAT solver.
That's for a counter for SAT.
Yeah. It's very slow.
So, by the way, the latest tool from their group is SDD, which you can also use to do counting, and we show.
Also, there's more recent work by Andre Ravelino, which uses pairing of counting and so on. So he also has a tool which does model counting.
Okay.
For SAT.
Yeah. Well, so, yeah.
In the last slide, you said you take the median of the samples. You sample cells, count them, and take the median.
Yeah.
Usually, one takes the arithmetic mean, the average. Why is the median better?
So honestly, I don't know why it is better, but the proof is very simple if you take the median. But I would guess that you can.
But you get better answers if you take the average.
You can do the proof even with the mean.
Yeah.
It's just that it gets a bit more messy.
Yeah.
The proof goes through.
No, but in the results, you get better answers if you take the average.
We didn't try that.
We didn't.
So the median actually, we knew that exactly these many solutions are above it. It would be, I know exactly T by 12 of it.
So basically, if it is wrong, then you know that half of them have to be wrong, and just a simple combinatorial argument. You can.
Also, the proof goes through. Just that
It's yeah. Okay, so how well we do in practice? We took benchmarks, we ran the exact counter, and we ran our experiments with setting epsilon to be 0.75, which loosely says that allowed error is 75%. What we observed in practice is that first the delta was set to be 0.9, but we observed that in all cases the count is actually within the 1 into 1.75 and over 1.75. So these two curves, the purple curves, are lower and upper bound, the 1.75 factor that you can obtain from exact counter cache. More interestingly, the error that we get is mean error is just 4%, which again says our guarantees are far more conservative than in practice. So we were allowing up to 75%, but actually the count that we come up with is very, very close to the exact count. Okay, so now moving on, can we take these techniques to cases where you are actually not interested in uniform sampling, but you have some distribution over assignments and you are interested in sampling from the distribution given some constraints. So extending the idea, what I want in this case is that all the cells should have equal weight. So what we assume here is that for every solution there is some weight assigned. It can be a black box, or you can specify according to different distributions. And now what we want is that every cell should have roughly equal weight. We have shown that this is actually possible. The proofs and the techniques extend. The idea is, instead of counting, now we'll be summing up the weights and using the similar ideas. So, and then we can pick a random cell. If we want to sample, then we'll sample this. In this cell, we'll sample a solution according to its weight. If we want to count, then we'll count the weight and multiply it with the total number of cells. So, moving on, one might be interested.
How do you do the, in the presence of weights, still just
Yeah.
partition it in the same old way?
Yeah, actually the proofs go through. There are more technical details, but I think we can take that offline. But yeah.
They're random constraints, so they have no preference for anything. So any line is as good as any other line.
Right, but now the number of solutions in each region could
Yeah, so
vary,
now
right,
you-
because of the weight. Like you could have one point with a very large weight and maybe another region with 10 points with small weights.
Yeah, so yes, so actually, so now the sizes of these random cells have to be,
Yeah.
they cannot be as small as they were earlier.
Yeah,
You have to make
exactly.
them bigger. And the factor by which you want to, are you going to talk about?
So
no,
what is the pivot, whatever it's called, equivalent to a pivot here?
So it is the earlier pivot multiplied by the ratio of the maximum weight to the minimum weight of any solution. So that's what we call.
Yeah, and but then you can do log reduction on that. So, yeah, I guess let's
But
check.
you're correct. The cells have now got to be bigger because
Yeah.
now you need a slightly bigger view, of slightly more global view of what is
Yeah.
going on.
Okay, so now one other interesting problem is that I'm actually not interested in sampling over all variables. Maybe I care only about few variables, or I'm interested in counting unique solutions to a subset of variables. For example, if this is my solution space for a formula over ABC variables, so I have three solutions: 0, 0, 1, 0, 0, 0, and 0, 1, 0. But if I ask how many solutions are unique solutions to A and B, then the number is only 2. Not 3. And actually, it's interesting that we can solve this case more efficiently, sort of violation of free lunch theorem, but we have to hash only on the variables over which you want to project. So doing that, your hash functions are actually more simpler, so we can solve this case. In general, the techniques you would have to enumerate, you would have to say, okay, I have to put a blocking clause on these variables, but we can solve it far efficiently.
So basically what you're saying is that you don't have to do a quantification first on the formula.
Yeah.
You don't have to do a quantification.
Yeah. And similarly, you can do sampling, you can give the guarantees that, for every solution. Okay, so the whole talk I kept mentioning hashing, and that's where the real meat lies. So I'll have brief discussion on this. So what are the hash functions we use? We use these XOR-based hash functions. What we were trying to do, we had n variable formula, so we are trying to partition the 2 raised to n space into 2 raised to m cells. So if our input variables are x1 to xn, how we construct the hash function is pick every variable with probability half and XOR them and equate that to 0 or 1. So that is one constraint. It divided into 2 cells. If you want to divide into, so if you recall in the algorithm, we had to keep dividing. So every time we add an extra constraint, it divides into 2 times the number of cells we have divided. So m XOR equations divide into 2 raised to m cells. So how does our formula look like? We have the initial formula and we have XOR constraints. Turns out that crypto people from crypto.
Sorry, I'm still trying to
Yeah.
digest this slide. So you have n, you have n 2 to the n in dimensional space, and so and you are doing m XOR equations.
Yeah.
That part I understand, but I haven't really understanding what each XOR equation is. So how do you pick one XOR equation?
So you look at all the variables, and for each variable you flip a coin. If it turns out heads, you say, I'll take this variable. Otherwise, I won't. You do this for everything, so you get a subset of the variables. just XOR these variables. These are all Boolean variables.
I see.
And then equate it to 0 or 1 with again probability half.
I see.
So it's basically divide. So the nice part about this is that it's
Oh, so this is a constraint.
This is a constraint,
I
and
see.
this constraint divides the space into exactly two halves, two equal-sized halves. Because for everything which makes it 0, you will have another thing which will make it 1.
Okay. Yeah.
So if you take any assignment of variables which makes it 0, just flip one of the variables and
I see.
These are two equal halves, but random halves.
So equating to 0 or 1 is also amounting to selecting one of the
Yeah.
buckets, is it? For hashing itself, you just leave it with the XOR.
Yeah. So that.
Leaving it with XOR will basically mean you are saying that I want this parity to be 1. Because all of this is going to be conjuncted with the original CNF and fed to the sensor.
No, but do you want a Boolean or do you want a hashing? If I want a result to be 0 or 1, then I just choose the XOR. The result is either 0 or 1. And that is a hash function to
Yes.
2 power 1. Right, so when you choose the 0 or 1, you are choosing one of the two buckets
Yeah.
also.
Yeah. Yes, you are choosing one of the two buckets. So we are saying that we are making a selection of which bucket.
Right.
Yes, absolutely. So that's how the random choice of the buckets come. Random choice of the cell.
Right.
Because
If you are trying to just define the hashing function, you wouldn't go through that. Right? You would stop.
Yeah, so just that XOR constraint is the hash function.
Right.
But at the end of it, I want to feed it to a SAT solver, and this,
Right.
whatever the SAT solver returns, it gives me the cell in the point in a bucket.
Right.
So yes, exactly. So by randomizing that, we are randomly choosing a bucket.
So every such constraint, right? I have original formula and I write m more such formulas.
Yeah.
And you fix those formulas once and for all, or do you keep regenerating those formulas? Like for
Adding.
example,
So we put the first one randomly generated. It cuts it into two halves. And by, as Rama just said, by picking it to be 0 or 1 randomly, we have actually identified one. So we count does that have more than 40 solutions. The moment we see it as 41 solutions, we say this is not good enough. Now we add another constraint, which is a fresh randomly.
but you
picked-
keep this constraint. On
Yes.
top of that,
Yeah.
you add one more.
Yes.
I see.
Yeah. So that also allows
So
for
that is
incremental.
what you were asking, is it a refinement?
Refinement.
Yeah.
Is it fine?
So the proof goes through. You don't need to.
Yeah.
Because we have independently chosen these two, right? And these are random.
So the other problem I have is that, when you do these two to themselves, now to me it seems like some of those cells will not intersect with the formula. Right? They'll be unsatisfied.
Yes. So some of the cells could be empty.
Could be empty.
For a
Yes.
specific case, for a specific choice.
Right?
But the
Probably that is low. Is basically what
Yes,
you're saying.
exactly. Because these are being randomly chosen, so there is no preference why a cell should have only empty things in it. It is as likely to have empty things as it is likely to have.
So that's 90% in practice.
Yeah.
Yeah. So
I'm-
that probability like 10%.
Okay, so while CNF plus XORs, and there's actually an efficient set solver, crypto mini set.
There will be some cells.
There may be some other cell.
But there may be only few such empty cells.
The XOR class is also converted to SAT.
No. In case of crypto mini set, people have observed that if you encode XORs into CNF, then it doesn't work so well. So what this nice solver does is that it is almost like an SMT solver, because XORs by themselves is a very easy problem, Gaussian elimination p-time problem. So and then it behaves almost like an SMT solver, and it can actually solve.
So you can actually take XOR constraints
Yeah.
like natively.
Yeah, native XOR. Yeah.
Write them out.
And
They do
it's
some-
that's an open.
Converting into CNF, actually, we also did the experiments. So I don't understand why, but the performance is far worse.
If you convert to CNF.
If you just convert it to CNF and just tell that here is a CNF problem, solve it. And if you say, okay, there are XOR constraints, can do Gaussian elimination on it. So of course, when there are XOR constraints, it is doing Gaussian elimination. figuring out. So I guess the moment you have some valuable variables, it's completely figure out that the other variables.
It's probably combining Gaussian.
It's combining Gaussian with
Yeah. So although adding on that, why XOR, we know there's a, for resolution based systems, we know there's an exponential lower bound for XORs. So the set solvers, although it's mess of a lot of things, but they do resolution. So that is that can be one of the potential explanations. One thing that
XOR algorithm, that's a different one.
Huh?
You have some XOR algorithm that was some
model group.
Yeah.
That's
Which
different.
uses the same constraints, same XOR constraints. That's why they call it XOR.
Yeah.
But they didn't do it. They didn't figure out the right pivot. They didn't figure out that we can randomly choose a cell and sample it out.
I see. They also choose these kinds of hash functions, but they do something else with it.
They use actually exactly the same hash functions, but they do not make use of the properties of these hash functions.
I see.
So
They don't
require
do this-
some
they don't do this counting and
complicated parameters to be provided, and if you provided the right parameters, then you'll get something otherwise.
But this is this.
Bart Selman and
Ashish Agrawal.
Yeah. Okay, so one of the observation is that what is the average length of a XOR constraint? If I have n variables, then average length is n by 2. In practice, there have been other experiments on XORs, and we know smaller the XORs, better the performance. So one of the questions was that how can we shorten the XORs? I'm not going into too much details, but what we came up with the concept of independent variables. What it means is that in a solution space, if you assign values to some of the variables, assigning values to some of the variables, which we call as independent variables, can uniquely determine values for rest of the variables. So, for example, if you are trying to encode a circuit C equals to A or B, then the independent support is A and B, because assigning to A and B, you know C, but assigning to B and C, you actually cannot uniquely determine what will be value of A. For example, this can be 1, this can be 1, and you don't know whether A is 0 or 1. In theory, finding independent variables complexity is we are working on it, but in practice it is easy because all the auxiliary variables that you introduce in any encoding, they are dependent variables. So we hash only on independent variables. The technique works as long as there is a superset of independent variables, and this results into a huge speed up. So wrapping up, where do we go from here? The first thing is all the techniques that I presented are on set domain, Boolean domain. Can we extend these to more expressive domains like SMT, CSP? I think there are two steps. One is efficient. We'll have to come up with efficient 3 universal or 3 independent hashing schemes. Just extending the bitwise to SMT, you can get the guarantees, but then you lose the whole advantage of SMT solvers because it will force you to bit blast.
So when you say SMT, what kinds of domains are you looking at?
To start with, I would say that bit vectors. Let's just start with modular bit vectors, and then we can extend beyond that. And the second thing is that in our case, we had crypto miniset which could handle this CNF+XORs very efficiently. I think to extend this, we'll need to come up with solvers which can also handle the hash function that will come up with very efficiently. So we'll need similar solvers for other domains. The other thing is we have been using CNF+XORs. It turns out that we don't know a lot about what happens when you mix CNF and XORs. For example, basic questions like phase transition. So we know that if you take a random CNF formula, there's a phase transition. If you take a random XOR, there's a phase transition. What happens when you have some predefined space and you are adding random constraints? If we know more, we can actually modify our algorithms to take advantage of such cases. The crypto miniset has more like a lazy approach. It tries to do Gaussian elimination. At some point, it does bit blast, but at very a higher depth. So more has to be certainly explored until what point one should do Gaussian elimination, when should one convert into And of course, one way to speed up the whole thing would be, can we come up with shorter XORs? There was a recent work from Herman et al. Which showed that if we knew more about solution space, shorter XORs would have been fine. But again, we don't know about solution space, so can we come up with, can we theoretically prove that even shorter XORs are fine? I also see there are some interesting connections which go back to and the paper by Jerome Valiant-Vazirani, seminal paper which reduced sampling to counting. So what the guarantees that we had were 6.84, and it is certainly troubling because why can't we get to 1? For almost uniformity that was described by Jerome Valiant-Vazirani, the factor was 1. What gets more interesting is that we actually get the approximate guarantees. If you remember, the factor was 1. So what Jerome Valiant-Vazirani showed is that if you want a almost uniform generator, you can make polynomial number of calls to approximate model counter, and then you can indeed get almost uniform generation. And vice versa, if you want approximate model counter, you can use almost uniform generator. So what we know is, of course, we can use the approximate model counter to get near uniform generator. So what we are doing are very similar techniques for both cases, but in case of approximate model counter, we are not using near uniform generator entirely as a black box. So what needs to be shown is that how much uniformity does one need to reduce to my approximate counting. So this is the part that of course you can get since near uniform generation looks like a weaker property than almost uniform generation, you can do the first step. We don't know about the second step. So what needs to be done is to get more explore the connection between near uniform generation and almost uniform generation. These are the work and the collaborators with which all of these works were done. Thank you.